Okay, in this video, we're going to start Chapter 7. We're going to be looking at a in-depth view of stereochemistry. We're going to see some subtleties in molecules that you've probably never seen before. So let's start by looking at these two molecules here, A and B. What they have in common is they're a tetrahedral carbon with 4 different things attached to it. So in A, I've just hypothetically used hydrogen and 3 of the halogens. Okay, so let's imagine that we have here a mirror. And this is our imaginary mirror right here. Okay? What does molecule A see in the mirror? It sees molecule B. Okay? Notice H to H, fluorine to fluorine, chlorine to chlorine, and bromine to bromine. Okay, bromine to bromine. Okay, no matter what you do, you can never lay molecule A perfectly on top or aligned up with molecule B. We say that these molecules will never superimpose. It's like your left and your right hand. No matter what you do, you cannot lay your right hand perfectly on top of your left hand or vice versa. Okay, so these are mirror image isomers. It's a very subtle type of isomerism. When two compounds that are mirror images of each other cannot be superimposed, we call each of those isomers enantiomers. This is a very important word, enantiomers, okay, which means mirror image isomers. Okay, we use the term chiral to refer to this property where the mirror image is not superimposable. Okay, and we use the word achiral to, and this is not a good word choice either. I'll explain that in a second, which means that something is superimposable on its mirror image. The problem with the word achiral in common speech is when you have a space chiral, when you say a chiral molecule versus achiral, it sounds the same, so people can't understand what you're trying to tell them when you use the word achiral. So I'm going to use the word not chiral instead of achiral, but achiral is technically the right word. There's some subtle differences between these terms, but the best way I can tell you that you can really understand this is that an enantiomer is a noun, and chiral and achiral are adjectives. Okay, you've encountered many things that are chiral in your life, okay? For one thing, you're chiral. If you stand in front of a mirror, you're right-handed, you watch yourself throw something. Don't actually throw it because you'll break the mirror, of course, but you notice that if you're right-handed, that person in the mirror is actually left-handed. Okay. There's other things in life that are chiral, like screws are chiral. Many branches of supermarkets are chiral. You go to one and the veggies are on the left, and then find another branch of the same store and the veggies are on the right, or things like that. Okay, so this just means merely that it cannot be superimposed on its mirror image. Okay, so that's chiral, and that's the simplest type of chiral molecule we have here, a tetrahedral carbon with 4 different things attached. Okay, so let's get into that. There's one tetrahedral carbon that has 4 different things attached, and this structural feature is called a chiral center or a stereogenic center. So right here, this is a chiral center. Okay. All right, when we make just two of those substituents the same, the molecule is not chiral anymore. So let's just imagine that I turned the fluorine into a hydrogen. And here's our situation here. Here's our mirror. Okay, and now I'm going to rotate along this axis right here. I'm just going to flop hydrogen up to here, and this will move chlorine and bromine over. Okay, so right here. And now I'm going to turn it around like this so that this hydrogen is over on this side. And what you see is that this molecule is perfectly superimposable with what we started with. Okay, so the chirality is eliminated when we have two identical substituents on our tetrahedral carbon. And I'm going to try to prepare another video where I have this program called Chem 3D where I'm going to actually show you some of these molecules superimposing. I realize that this is one of the limitations of this narrated PowerPoint is that I can't actually superimpose things for you, but I'll try to do that, and it'll be the third video in the series. Okay. All right, so let's look at a more encompassing definition of chirality. A chiral molecule has no plane or center of symmetry within the molecule. All right, so let's look at this molecule we just looked at. All right, if we take a plane, and it takes 3 points to define a plane, so these are the 3 points that are defining our plane. We say that this is a plane of symmetry because everything above the plane looks just like everything on the other side of the plane. Here I'm going to draw it so chlorine and bromine are kind of level, and you can see that the hydrogen sees exactly an image of itself on the other side of that plane. Here is probably the best way to represent it. We're saying that the white screen here is a plane of symmetry, and you can see how the hydrogen sees the same hydrogen on the other side of that plane right there. Okay, so if something has no plane of symmetry within the molecule, it's chiral. All right, so let's imagine that this hydrogen, we'll just make it as simply a deuterium. All right, this is now not a plane of symmetry anymore. Okay, it's no longer a plane because there's something different on one side versus the other. Okay, and you can see that here most easily that the two sides are technically different. Okay. All right, so let's look at a few other molecules and see if they're chiral. All right, so this molecule here, which is cis 1,3-dichlorocyclopentane, we actually have a plane of symmetry right there that goes up and down, straight up and down over that line, right? So the chlorine sees the other chlorine on the other side of that plane. So this molecule is not chiral. All right, let's draw its mirror image. Here's its mirror image of this, is this over here, right? So it's no longer chiral. So it's the mirror image. But all I got to do is just flop this sucker over, right? We'll just say I have a axis like that. And I'm just going to flop it over. And of course, I get an image of the molecule that looks exactly like itself. Okay? Now, here we have the trans isomer. And that same plane of symmetry is now not a plane of symmetry anymore, right? Because chlorine's on one side, and on the other side of that plane it sees a hydrogen. Same vice versa over here. So what we identified as a plane of symmetry in the cis is not a plane of symmetry in the trans. We have an axis of symmetry because we can rotate around just like that, and we get an equal representation of what we started with. We'll say that we're rotating on the z-axis. That's the Cartesian axis coming straight at us. But the definition of chirality is there's no plane or center of symmetry. A center of symmetry is kind of a hard thing to do in an organic molecule. I'll try to maybe when we're looking at questions at the end here, we might look at a molecule that has a center of symmetry. But the plane of symmetry is really what you should be focusing on. That's the most common situation where you're going to have chirality or lack of chirality. So an axis of symmetry doesn't count. If we draw its enantiomer, which is down here, let's see, kind of, yeah. Right, so here's an imaginary mirror right here. Okay, if you look at its enantiomer, it will never superimpose on itself. Okay? So because of that, we can't superimpose the enantiomer. It is not, or it's a chiral molecule. Okay? Alright, so here's a problem. Do this one yourself. This is a very classical type of problem, and I'm going to go straight through it, but you should pause it and do this first. Determine whether each species below is chiral, and place an asterisk beside all of its chiral centers. Alright, so if we look at the answer to these, of course, the first one is not chiral because we can draw a plane of symmetry right down the middle like so. When we put this double bond here, this plane of symmetry is gone, and we now, this is now a carbon with 4 different things attached. Let's just look at it. It's got hydrogen, chlorine, CH2 with an sp2 carbon, CH2 with another CH2. So they're technically, it has 4 different things attached. Alright, this one is achiral because of the location of this double bond. It still maintains a plane of symmetry in the molecule. This is a classic trick question, but the molecule generally has to have tetrahedral carbons to be chiral. We'll see a couple of exceptions to that a little bit later in the class, but generally molecules that don't have an sp3 carbon, you don't need to consider their chirality. In this next one, we have a plane of symmetry. I'll just define the 3 points of this plane here. Halfway between those carbons and this carbon right here. If we look at the plane there, everything on one side of the plane is the same as on the other side of the plane. I've tried to draw the plane there, but hopefully you can sort of visualize it that also, let me see, yeah, this plane is also defined by these 3 points as well, just slicing through the hydrogen, chlorine, and the carbon atoms connecting them. Everything would be the same on one side of the plane or the other. Alright, so in this next molecule, we've sort of taken this one right here and just added a methyl group to it, but that destroys the symmetry down here. Okay, and the plane of symmetry that we identified here is not a plane of symmetry here, so this is a chiral molecule. Alright, in this one we shortened the ring by 1 carbon. We've eliminated this CH2 group right here, and what you see here is that we now have gotten rid of our chirality. This is an achiral molecule because you can have a plane of symmetry straight down the middle. Okay, this next one is an achiral molecule. We'll say that this is what we suspect as being our chiral center, but it really isn't because it's got 2 methyl groups on it. So because it has 2 identical groups, it does not have a chiral center, and it's not chiral. All of these substituents here are CH2 groups, and the mere fact that they have 2 identical groups at each carbon here rules them out as a potential stereocenter or chiral center. Okay, this one right here is chiral. this is our suspect atom, but we see we have methyl, ethyl, and propyl. We have three different groups, or sorry, four different groups if you include hydrogen there. And the next one is also achiral because we can't really identify any carbon atom with four different things on it, right? This is a CH2, two hydrogens. This is two chlorines on the same carbon. And the others are methyl groups which have three identical substituents, so they can never be chiral. Okay, here's another problem. Let's just take cocaine here and identify all of the chiral centers in cocaine. All right. All right, so you don't do anything with sp2 carbons, and oxygens are not going to be chiral either. Okay, so these are our four chiral centers in cocaine here. There's our fourth substituent. It's a hydrogen in each case, but it's not shown because of the proper bond line diagram. Okay? All right, so, and we'll take up much later in this class the nuances of molecules that have multiple chiral centers in them, but right now for cocaine all we did was just identify them. Okay, let's look at the physical property that allows us to identify enantiomers, and I'm going to talk a little bit about the historical significance of this as well. Back in the 19th century, one of the ways people would characterize compounds was by whether or not they could rotate something called plane polarized light. Okay, so here's what plane polarized light is. All right, so light is has a source here, and the wavelengths are going in all directions. So it's going straight up and down. Some of them are coming straight forward and backward. Some of them are at intermediate angles, and they're represented by these vector arrows here. Each represents the direction of the light. So that's our dirty, unfiltered light. Now it's going to go through something called a polarizing prism, and that's going to get rid of all the orientations except one. Okay, so now it's only, I guess we'd say it's all the light has been filtered out except all of the light that's along what I guess we'll call it the y-axis here. Okay, so this light is now going to go through a sample tube. This is called the polarimeter tube. And what the people noticed way back when was that some compounds would cause the orientation from like 100% the y direction to something off of the y direction, like you see here. Okay, so it would change the orientation of the polarized light. So if it caused the polarized light direction to change, it would be considered optically active, and most of the optically active compounds were, well, they were all exclusively derived from living systems. The optically inactive compounds don't cause any sort of rotation in the orientation of the plane, and these were mostly inorganic compounds, and actually a lot of organic compounds too were optically inactive. Okay. After taking into account the fact that we have different concentrations in this tube, and sometimes people were using tubes of different lengths, this equation was developed where we just factor out those different path lengths and concentrations. And this value here is called the specific rotation. It's a property for any optically active compound. Okay, and that's the symbol used, alpha in brackets with the symbol D. And the light here is the sodium D line at 571 nanometers. That's the standard light frequency at which rotation is measured. Okay. All right, so Pasteur was the first person to really discover what was causing optical activity. He's actually a chemist that worked for the French wine industry, but he's sort of been claimed by the biologist for his development of a rabies vaccine, but he was really a chemist. Okay, so he worked for the wine industry, and he was crystallizing sodium ammonium tartrate. And kind of by some strange accident, he looked at his crystals under a microscope and noticed that he had two types of crystals that were mirror images of each other, and the crude representation of them is depicted here. So he did kind of a very tedious thing. He took a pair of tweezers and separated the mirror image crystals, and he now had two piles of crystals, one of one mirror image, one of the other mirror image. And he took pile 1 and pile 2 and noticed that they were almost identical in every one of their properties except their specific rotation. One of them was plus 12 degrees and the other pile was minus 12 degrees. Okay, Pasteur hypothesized that since the crystals were mirror images, that the molecules making up the crystals were also mirror images. It turns out that that somewhat naive hypothesis actually turned out to be correct. And from here we have the famous relationship that if two compounds are enantiomers, they will have equal but opposite specific rotation values. This is a property of enantiomers. Okay, if one of them is plus x, its enantiomer will be minus x. Okay, so this was a very important discovery here. Okay, so one isomer or one enantiomer is going to rotate in a positive direction, and we call that one the dextrorotatory. Sometimes you'll see the prefix D, but that means something a little different, but it is derived from the fact that most of the molecules from which D was developed did have a positive rotation value. The difference is a little different between D and plus. We'll talk about that in chapter 23, which I guess if this is chapter 7, that's a long time in the future. If you take them in sequence, that would be April or something like that. All right. Minus isomer is called levorotatory, and often the prefix L is attached here, but like we'll see, L means something a little bit different than the direction of the specific rotation. All right, so plus and minus are experimental numbers. You can't get any structural information. The only structural information you can get is that if you have the structure of one and you know it's plus, you know that the structure of its enantiomer is minus. Okay, a one-to-one mixture of enantiomers is going to be optically inactive. This is because the rotation done by one is undone by the other. And this has a special name. This is a term you have to become very familiar with: racemic mixture or racemate. It's a one-to-one mixture of two enantiomers. Okay, and it's optically inactive. It won't cause any sort of rotation of plane polarized light. Okay, so a compound is optically inactive if it's a pure single enantiomer, or if it's a mixture of enantiomers that's not one-to-one, and this is scalemic. Generally, the specific rotation that you see reported is the property for a pure enantiomer. Okay. All right. So Another form of nomenclature for chiral centers is the RS nomenclature, and this does convey structural information. Okay, you can describe a chiral center by its R or S configuration. So let's look at how we assign an R and S configuration. All right, for step one, we're going to assign Kohn-Ingold Prelog priority numbers. These are the same ones we use to assign the E and Z configuration for alkenes to each of the 4 substituents attached to a chiral center. So we're going to look at the molecule alanine, which is over to the right. Okay, and let's just do this. This is a very simple amino acid. All right, so at the chiral center we have a methyl, an NH2, a carboxylic acid, and hydrogen. Nitrogen is higher than carbon, and of the 2 carbon substituents, the carboxylic acid ranks higher than methyl because there's oxygens at that carbon, whereas the methyl only has hydrogens, and the hydrogen at the chiral center is priority 4. Okay, step 2, orient the molecule so that priority 4, which is more often than not, it's a hydrogen. It doesn't have to be, but in more than 90% of the cases it is a hydrogen, is to the back. Okay. Step 3, you're going to draw an arrow that goes from 1 to 2 to 3. If the arrow goes clockwise, it's R. If that arrow goes counterclockwise, it's S. So there's the arrow we have there, and you can see a nice clockwise arrow going from 1 to 2 to 3. So what I have drawn there is, of course, the R enantiomer. Let's now do it for this compound down at the bottom. Okay. So here's our chiral center, right here. And chlorine is our highest priority. C double bond O is next. CH2 is after that. CH3 is dead last. Okay? So our priorities are 1, 2, 3, and 4. Okay, this one is not quite as easy because priority 4 is coming out at you. It's not going to the back. So we have to flip our molecule over so that it is to the back. All right, so now when it's to the back, you can draw your arrow, and if you draw the arrow from 1 to 2 to 3, it's also a clockwise arrow, and this is another example of the R configuration. All right, some of you probably figured this out, but you may say, what if I'm too lazy to flip it over? Couldn't I just assign the configuration that way, and noting that after I draw my arrow that I'm 100% wrong, and then just call it the R isomer? Well, yeah, you can do that, but you have to be very careful. I advise you not to do that in the beginning, but I guess it's a shortcut that a lot of us take. So what would happen here? We draw an arrow that went from 1 to 2 to 3, right? And it looks like an S arrow, but we know not to call it S because number 4 is coming out, and so we would call it R. Okay, all right, so that's another way you can do it, but again, be very careful if you adopt that system. Okay, so here's a problem here. We're going to assign the RS configurations to each of the chiral centers. Whoever set up this problem is a very nice person because they drew the priority 4 hydrogen substituent to the back. So you don't need to do any of the orientations. The complication here is that there's 2 chiral centers. All right, so you should do this problem yourself, but let me just tell you, do each chiral center one at a time. Don't try to see this molecule as one whole entity. You've got to do 2 separate operations. The other problem is another type of problem we'll do later, and it's to draw R3-bromo 1-butene. Okay, So if we draw this molecule, I'm going to draw the chiral center on the left. It's got an OH, it's got a hydrogen, it's got a COOH, and it has the rest of the molecule. All right, so we have 4 substituents at our chiral center: OH, H, COH, and the rest of the molecule. All right, so if we rank these, this is number 1. Okay. The double bond, remember, we're going to, let's just draw this out, sorry. We're going to pretend that that is the equal number of single bonds. So because this has like 3 oxygens and this one over here only has 1, this is going to be number 2. And this is going to be number 3. Okay? And hydrogen, of course, is going to be number 4. So that's how you have to do this. And you have to take a similar approach to the other chiral center. I think it's actually a different slide here, so I can go ahead and draw anything anywhere I want here. All right, so in this other chiral center, it's methyl, OH, and the rest of the molecule. So OH is number 1. The rest of the molecule has an oxygen on it, whereas this is just a methyl which has only hydrogen, so the remainder of the molecule is number 2, methyl is number 3, and hydrogen, of course, is number 4. Okay, so if we understand that, we can very easily assign the stereocenters, right? The one on the left is S, 1 to 2 to 3. The one on the right is R, 1 to 2 to 3, in a clockwise direction. So if we had to name this, I realize that naming carboxylic acids isn't for a long time in your future, but it would be something like SR23-dihydroxybutanoic acid. Or, or 2S3R dihydroxybenzoic acid, or butanoic acid. Okay, all right, so we have to take the chiral centers and do them one at a time. All right, so let's draw R3-bromo-1-butene. A lot of times on exams I put it like this, just finish my drawing. This is because the classes are kind of large and I'll go crazy if I have to see every possible orientation of this molecule, so I would like to just restrict it to 2 answers. Okay, so it says that I want the R, so that means whatever I have to have has to have bromine is going to be 1. If we look at the molecule, we have this group and a methyl group, and we know that the vinyl group, or the alkenyl group there, is going to be 2. That's going to outrank the methyl group. Okay, so if I want it to be R, I have to have 2 over here on the right and 3 over on the left. Okay, so R, 3-bromo-1-butene, is this compound right here. Okay, and again, I tried to just restrict the number of possible orientations, because if you have to assign the R and S for every exam paper yourself, it gets to be a bit of a tedious process. Okay, let's look at another way to generate or to depict chiral molecules. All right, so this molecule here is R plus lactic acid. Okay, let's just verify that it's R. I'm going to rotate it around the y-axis shown here, and that gives you this. And I'm going to do just a very slight rotation so that hydrogen is perfectly to the back. So you can see here that OH is 1, COH is 2, and this is 3. And our arrow is going in a clockwise direction. All right, so if I take my original drawing here, you can represent it this way, and this is called a Fisher projection. Okay, and in a Fisher projection, it means that the horizontal groups are coming out of the paper and the vertical groups are going back into the paper or back into the screen. Okay? Many of the chiral molecules are biologically important, biologically derived, and the convention for biomolecules that contain C double bond O groups is to put the C double bond O group as close to the top of the skeleton as you can, and that the carbon skeleton should be vertical. So this is the proper way to represent R plus lactic acid. Okay, plus lactic acid. If that's all you said, you say, well, I can't tell what the configuration is from a plus sign, but you can tell what the configuration is from the R that's in front of it. Okay, we have to be careful with Fisher projections because they're not real. We know that the bond angles at tetrahedrons are not 90 degrees, and they're not flat molecules either. Okay, so look what happens if we take that molecule, and I'm going to rotate every one of these carbons, or every one of these substituents by 90 degrees. What happens when I did that? Okay, this is the molecule that you end up with. But when you turn it back into a three-dimensional structure, it's now the S enantiomer. So why did this mess up? Well, it has to do with the fact that a Fisher projection is not real. Carbon is not square, planar, flat molecule, so you can't do these rotations. Okay? So what looks like a rotation isn't really a rotation at all, because not only were we rotating, but we were also changing. So methyl here was vertical, it was going back, so methyl is now coming out. So that has changed the configuration. So there are certain things you can and can't do with Fisher projections. And one other thing about the Fisher projection is that as long as hydrogen is on a vertical, that means it's to the back, so you can go ahead and assign its configuration on the Fisher projection. Alright, so that's S like we saw before. This one, you can't do that because hydrogen's on a horizontal. Okay, but you could do that trick I told you. You could go ahead and assign it and just remember that you're 100% wrong and just write the other answer. But again, always be careful with doing that. So what can you and can you not do with a Fisher projection? Okay, all right, so there's the repeat of that statement I just said. If priority 4 is on a vertical, an arrow going from 1 to 2 to 3 will give you the correct RS configuration. All right, you can't rotate by 90 degrees or you can't exchange two substituents. That will change your configuration, okay? So we just saw what happened when we did the 90-degree rotation. Okay? Here, what we're doing is we're exchanging what are we doing here? We're exchanging the location of CH2OH and COH. In both of these here and the original one, we had the configuration where hydrogen was on a vertical, so we could go ahead and assign the R and S. And here, now when you assign it, you see how you turned R into S, okay? And here's the same, another incident of a 90-degree rotation, showing how that also screws up the configuration. All right, so what can you do with a Fisher projection? Okay, you can rotate it by 180 degrees, and that will not change your configuration. And of course, most of you probably know from a long time ago that 90 twice is 180. So the reason why 180 works is because you screw it up totally when you do 90. But then when you do another 90, you screw up the screwed up one, so it's back to where it was in the beginning. So what you've done here is, I guess, two wrongs have made a right in this case. That's why you can rotate by 180 degrees. Okay, the other thing you can do is you can hold one of them constant and rotate the other three. So imagine that I'm taking this hydrogen, I'm going to hold it constant, and over here I'm going to rotate each of the other three groups. Okay, I'm going to rotate COH there, CH2OH there, CH3 there, and I haven't really changed the RS configuration at all. Of course, you see kind of that if I move them all in the same direction, or move three of them in the same direction, of course I'm not going to change the RS configuration because my arrow is going to go the same way, clockwise or counterclockwise. Okay, so the 90-degree or exchange of two is an illegal operation, but the 180-degree or hold one constant and rotate the other three are both legal operations of Fisher projections. You will not change the configuration from 180-degree rotation or holding one constant and rotating the other three. Okay, so let's assign the R and S configuration to the Fisher projections. The one on the left, all I have to do is assign the priority numbers, right? So nitrogen is 1, CF3 is going to be 2, and this is going to be 3, because fluorine, having 3 fluorines, each of the, all it would take would be 1 fluorine to outrank all the oxygens. Okay? So we just assign it like so, and that is the R configuration. All right, this next one, we can't do this direct assignment because the hydrogen is on a horizontal. Okay? So we got to do some sort of legal operation to get hydrogen vertical. There's two solutions. One is to do a legal operation to get hydrogen vertical and then assign the R and S configuration. The other thing is to go ahead and assign it, and then remember that what answer you're going to get is going to be 100% wrong because hydrogen's not where it should be. But as long as you remember that you're wrong, you'll be okay. I recommend in the early stages that you not consider the second one. Okay? Again, if you feel confident, go ahead. All right, so let's look at each case. Approach number 1. The easiest way for me to do that is to hold chlorine constant, or I could hold anything except hydrogen constant, but I'll say I'm going to hold chlorine constant, and I'm going to rotate each of the other three. Okay, so I'm going to rotate COH where CH2OH is. Okay, here's my rotation. That's going there. This is going here. And hydrogen is going to the top where it needs to be for a reliable R and S configuration assignment. Okay, chlorine's 1, carboxylic acid's 2, CH2OH is 3. The arrow from 1 to 2 to 3 goes in a counterclockwise direction. Therefore, this is the S enantiomer. Okay, what about approach 2? All right, I can go ahead and assign 1 to 2 to 3. My arrow goes in the clockwise, but I know that since hydrogen out, that has to be the wrong answer, so S is therefore also arrived at by doing it that way. Okay, whatever you feel comfortable with, is okay. I guess you do always have, if the question is assign the RS configuration, I guess a person that knows absolutely nothing does have a 50% chance of getting it correct. Okay, I think this is where this video is going to end. Yeah, so let's end there, and we'll start the rest of this chapter in the second video.